think you might have an idea.
It's like a 6.
Okay, good morning everyone. Good morning. So we were starting our discussion on transient conduction last class. I want to go deeper in that today, and hopefully by the end of lecture today we will have a method for solving problems, and I'll solve one problem on Monday for the first half of the lecture, and then we'll start radiation after that. Okay? All right. Your homework has been posted. I posted it yesterday afternoon, so please take a look at it. They are not easy problems. If you do have questions, feel free to ask me. Okay? I have office hours today as usual. All right. From last class, let me reduce the volume a little bit. Okay, so from last class, zero-dimensional unsteady conduction. This was the equation we ended up with. Okay, so the situation was depicted in the following manner. We had this lump essentially of a body which was sitting in a tub with ambient fluid, and we had assumed that the temperature of the body or the lump was lesser than the ambient temperature to begin with. Less than T infinity, and then we used the first law and obtain the following differential equation. Okay? So tau d theta by dt plus theta is equal to 0. This is in the absence of energy generation. So E dot G is 0. We will include that eventually. It's not a big deal, it's just a constant. And we had also assumed that the temperature gradients within this body, within this lump, was essentially 0, so that the temperature is a function of time only. Theta T of t minus t infinity. This is just a change of variables. What's the reason for doing that? It's just that the solution comes out to be written out much more compactly. Okay? And it is much easier to do the substitutions and so on. It is not a big deal if you just leave everything in terms of t of t. So the solution ends up being the following. Theta by theta naught is e to the power minus t minus t naught by tau, where tau is the thermal time constant, is given by the following ratio: rho c LC by H, rho being the density, little c is the specific heat capacity, and LC is the characteristic length. And I'm going to write down LC as the ratio of the volume to the surface area. So somewhere here, LC volume to the surface area. Okay, that's an important parameter. This is an exponential solution. You've seen the likes of this before in system dynamics, and perhaps in other classes as well. So the solution behavior should not be surprising. Start at some initial condition, reach a steady state. Okay. Now the big question is, okay, and I think I went a little further than this. I said that the ratio t minus t naught by tau can be written as the following grouping: h LC by k multiplied by K by rho C T minus T naught by LC square. The first grouping is your Biot number. So this is Bi Fo. The Fourier number and the Biot number. It is quite evident that the Fourier number contains the time variable, and so the thermal time constant tau is inversely proportional to the Fourier number. The larger the Fourier number, the smaller is the thermal time constant, which means the system is more nimble. The system response is going to be much quicker. If the thermal time constant is large, the system is going to respond in a very sluggish manner. Okay, so if the Fourier number is large, tau is small, it's a nimble system. Fourier number is small, the thermal time constant becomes large. You can see the inverse proportionality. The system is sluggish. And depending on its application, you want one or the other. Okay, it's completely dependent on that. And we spoke about some applications of transient zero-dimensional conduction heat transfer as well last class. The big question though is, okay, this Biot number, named after the French physicist Maurice Biot. Maurice Biot was one of the seminal figures in mechanics and thermodynamics. Okay, the whole field of plasticity theory in mechanics, which is my field of research, it owes a huge debt to Maurice Biot. Of course, we are also learning about him in fluid mechanics and heat transfer. So, several spans of influence. Okay? So our biggest concern here is, okay, you just take my word as a matter of faith and say, all right, let the temperature gradient be uniform within the body. I have zero-dimensional conduction. When is this possible? Under what conditions is this really valid? Or is this just a figment of my imagination? So we have to unpack that information. Okay? And the clue lies with the Biot number, what the Biot number espouses. And we want to see what it really tells us in terms of the approximations we can make. Very simply, put from last time, the Biot number you can think of as a dimensionless grouping of the thermal resistance to conduction and thermal resistance to convection. So I want to write that down here, which is H LC by K is 1 by HA, and then K by KLC by A. This is our conduction. Our convection, if the Biot number is very, very small, this means that the thermal resistance to conduction is very, very small. And so you can approximately say that the temperature gradient within the body is negligible. That's the whole upshot of the argument that we're going to make. Okay, but the thing is, we have to prove that the Biot number has to be small, and this is at steady state. You see, I'm defining the thermal resistance to conduction and convection. These are steady state definitions. I'm looking at a transient problem. So what gives? Okay. So to understand this, I'm going to look at one-dimensional unsteady conduction. So our question or our challenge, under what circumstance can we say, or can we ignore temperature gradient within the within the lumped body. It's like a lump of clay, essentially. Okay? So under what circumstances can we ignore it? The clue lies with unsteady conduction. And let's start off by thinking of a very simplistic scenario. Okay? So here, temperature is a function of both the spatial dimension as well as time. Alright? And I'm going to consider a very simplistic situation. This problem can be solved for a variety of boundary conditions and so on. I'm going to consider a plane wall. It's a slab, essentially. And I'm going to say that before time starts, maybe there was some heat generation within the body. And so the profile at time t is equal to 0, just before time starts, is some kind of a parabolic distribution of the following sort. So this is my initial condition. This is at t is equal to 0. Initial profile. Okay. Let's say the t infinity is the same on both sides. So before time started, there was some energy generation within the body. Then as soon as time starts, I'm switching the generation off. I'm starting off with this parabolic profile. It is symmetric about the center line, because I'm assuming it to be the case, so that the temperatures at the outer edges are the same at all instances in time. So this is the center line. X is equal to 0. X is equal to plus b. X is equal to minus b. Okay, where plus b and minus b are the half width of this plane wall. And so if I draw the temperature profile, obviously this is going to be the profile initially. Then what happens as time starts, because the ambient is cooler and I started off at a hotter temperature, I'm going to slowly start seeing that this temperature is going to not only reduce in time, but the curvature is also going to start increasing. Okay? Or the radius of curvature is going to start, the curvature is going to start decreasing, or the radius of curvature is going to start increasing. So at some time after the start, this is going to be my profile. After a certain period of time has elapsed, this is going to be my profile, and eventually I will reach steady state. I will just get a flat line where the temperature is T infinity everywhere. Okay? So this is the temperature profile. So this is T as a function of x and t, and then this is T at T tending to infinity. Does this make sense to everybody? Symmetric. The boundary conditions on the edges are the same. And the reason why I'm trying to implore symmetry in this problem is so that I can work with only one side of the problem. The other side is just a reflection of the events on the other side. Okay, so I'm going to look at this side here. Okay, so this is the side I'm going to be interested in. It's one-dimensional, unsteady conduction with no heat generation. So I'm just switching it off once time has started. Q dot is 0 every time for T greater than or equal to 0. And so, for the symmetric case that I'm considering, for 0, x, and b, and for t greater than or equal to 0. In reality, I should say 0 plus, because 0 minus is when the heat generation is switched off. Okay, but we will not be bothered with these niceties. We will assume continuity between 0 plus and 0 minus. Okay, so under this situation, I'm looking at the energy balance within the body And I'm essentially going to recall the one-dimensional heat diffusion equation. 1D HDE Q dot is 0. Unsteady, so my derivatives will be partial derivatives. So if I write it out, it's K d square T dx square is rho times C dt by dt. I'm going to rearrange the terms. So d square T by dx square is rho C by K, or 1 by K by rho C dt by dt. K by rho C is the thermal diffusivity alpha, so I can write this as the following. This is a partial differential equation of order 1 in time and order 2 in the spatial variable. Okay? I need to prescribe three things: an initial condition and two boundary conditions. So initial condition at t is equal to 0, let's just make life simple, say t is equal to 0. T of 0 and x, or x and 0, is some t naught, okay? Or we will bring back to the non-dimensional or the change of variables thing. So we will say that theta at x comma 0 is some theta naught, where theta is t minus t infinity. Theta is a function of x and t here. Okay? So I can rewrite my ODE, I'm going to do that in a second. Then I'm going to have boundary conditions. So this is initial condition. Boundary condition. Due to symmetry of heat transfer, the flux at the center line is 0. Symmetric boundary conditions, as you can see there. Right? The slope is 0 there. So at x is equal to 0, dt by dx, which is the same as d theta by dx, theta and t being functions of x and t, time is 0. This is the boundary condition. Third boundary condition is that at x is equal to plus b, I am open to ambient atmosphere. So at the conductive flux coming out is equal to the convective heat transfer flux. So minus k d theta by dx at x is equal to b is h times theta at x is equal to b. Looking at convective flux, okay, and conductive flux. So these two are my boundary conditions. And the PDE recast in this change of variable form. Theta this is our PDE. So we have to solve this, which I will partially do because it's a partial differential equation. And then we will glean some information from it. Okay? To solve this PDE, we will use what is called as the method where you have this written as a homogeneous function of the position and a homogeneous function of time, so by separation of variables. Okay? So I'm going to say theta of x comma t is going to be written as a function of x and some unknown function of t. Okay, so they're both homogeneous, they're not mixed. F is a function of x only, g is a function of t only. This is a solution candidate. Okay, This is called variable separations. So if I take the derivative of theta with respect to x, the spatial derivative, d square theta by dx square, the only quantity there that's going to be undergoing a derivative is f of x. So I'm going to call it as f double prime, where the prime indicates a spatial derivative. And then if I do the derivative with respect to time, the only quantity that undergoes derivations is that g of t thing there. F of x g dot of t, where the dot, say time derivative. Okay, so the dot is on g, the spatial derivatives is on f of x, and I'm going to take this, plug it back into the ODE. So substitute into the PDE, I'm sorry. If I do that, I end up getting the following. So f double prime g of t is 1 by alpha, d theta by dt is f of x g dot of t. Or I can write it in the following manner. F double prime of x by f of x is 1 by alpha g dot of t by g of t. And if this has to be true, then it implies that the ratio of these two quantities that you're seeing on the left hand side has to be equal to a constant. Okay, f is a function of x, g is a function of t. If I take two variables that are functions of x and equate that to a ratio of two variables that are functions of time, and if they're equal to each other, then that ratio has to be a constant. No other way can they be equal to each other. Okay, so this can be a constant plus or minus some lambda square. Okay, so this is a constant. And for reasons that will be very obvious, very soon I'm going to consider the ratio to be equal to minus lambda square. Okay, so say we choose the ratio to be minus lambda square. Once we do that, I end up having the following. They're both the same. I look at the first one, cross multiply. What does it remind you of? If you just ignore the fact that it's a function of x, call it as a function of time t. That's a second order ordinary differential equation that signifies harmonic motion. The solution is going to be sinusoidal. Okay, so this is just a spring mass system oscillating if I assume that the x is time. And likewise here, g dot of t plus alpha lambda square g of t is equal to 0. This is just a first order ordinary differential equation in time. Fairly straightforward. Exponential solution is what is expected here. Now you see the choice for the lambda being negative, because if I solve this, the solution is going to be e to the power minus lambda square times alpha times t. And by the basis of what we assumed, the temperature is dropping down as a function of time. Okay, so if I solve these two, and I'm not going to do that explicitly, should be fairly evident. F of x is some C1, C2, sine lambda x. That's the solution. You can check it up and see if it satisfies, and it will. And g of t is some C3 e to the power minus alpha lambda square t. Once again, you can satisfy that by substituting. And so, theta, which is a function of f of x and g of t, okay, if I combine them together, that's C3 minus alpha lambda square lambda x sine lambda x. C3 is a constant, C1 is a constant, C2 is a constant, lambda is a constant. I'm going to take this C3, bring it into the bracket here, and call C3 times C1 as some big constant capital A. C3 times C2 is some other big constant capital B. And so theta of x comma t becomes e to the power minus alpha lambda square t capital A capital B sine lambda. Where capital A is C1 times C3, capital B is C2 times C3. Alright, so I have, after all this hard work, I have three unknown constants in this solution. Lambda is a constant, capital A is a constant, capital B is a constant. I need three conditions. I have the initial condition and I have two boundary conditions. So I can completely solve this system, which is good news. And once again, keep in mind, why am I doing all this stuff is because we want to come up with a way of saying, okay, under what circumstance can I say that the conduction can be zero dimensions? Under what conditions can I say that the spatial dependence can be neglected? I can tell you the answer and move on with it, but this is better. Okay? This gives you the mathematical basis for ignoring it, and then we also talk about the physical basis for ignoring it. Alright, now we start substituting. So boundary condition d theta by dx at x is equal to 0 is 0. I'm not going to do the substitutions. If you do the substitutions, you'll figure out that capital B is 0. I'm going to do the second boundary condition. Okay? At x is equal to b minus k is h times theta at x is equal to b. So first thing I found out is that this capital B is gone, so my solution has drastically simplified to two constants. If I do the substitutions here, d theta by dx, if I do the substitution, that's differentiation of cosine lambda x, which is minus lambda times sine lambda x. When x is equal to b, I substitute, and I get this as minus k e to the power minus alpha lambda square t. Cannot do much about that. Okay? Times minus lambda sine lambda times b. This is equal to h. Cannot do much about that either. Then e to the power minus alpha lambda square t. Cannot do anything about that. Theta at x is equal to b is cosine lambda b, where b is the half width of this plane wall. Cancel, cancel without any loss of generality. So I have the following: cosine lambda b is equal to k lambda by h sine lambda b. Cosine by sine is cotangent, so this is cotangent lambda b is equal to k lambda by h. I'm going to do the following now. Multiply by b, multiply by b, where b is my characteristic length now. It's a ratio of the volume to the surface area available for heat transfer, because this is a plane wall. Volume of a plane wall is area of surface area of heat transfer multiplied by the width. Okay, surface area is there, and so essentially I'm looking at little b as the characteristic length. And so if I look at this now, I end up with the following. So cotangent lambda b is lambda b divided by, think of this b as a characteristic length and rearrange it as hb by k. Do you recognize this creature in the denominator? The Biot number. Okay, so suddenly it makes an appearance. It's actually lambda b by the Biot number, but of course that doesn't tell us what the solution is. We have to suffer some more. And some of you may realize that this equation is called as a transcendental equation. A transcendental equation is an equation where you have an algebraic part, which is lambda times b, and you have a part like a cosine or a sine which cannot be expressed as a polynomial function. Okay, and it has some nice analytic properties and so on. We will not get into that. The upshot is that there are an infinite number of solutions for this particular problem. And I'm going to plot them. Okay, so this is first of all called a transcendental equation. It will lead to a Fourier series type solution eventually. We're not going to go there, trust me. To get a characteristic nature of the solution, I'm going to plot two things. As a function of lambda b, you see cotangent is a function of lambda b. The quantity on the right hand side, lambda b divided by this constant, is a function of lambda b. So if I plot both of these as functions of lambda b, this line here is going to be lambda b divided by the Biot number. When lambda b is 0, that quantity is 0. When lambda b starts increasing, this is going to increase linearly. The Biot number is just a constant. It does not do much to it. It's a scaling parameter. Cotangent is a function where you reach infinity at lambda b is equal to 0. When lambda b is equal to pi, you go to infinity. And so if I plot this as 0, pi, 2 pi, 3 pi. When I'm at pi, I go to negative infinity because sine pi is minus 0. And then I have 2 pi here and 3 pi and so on. So it's going to look like the following. And so on. So these are cotangent lambda b curves. And the points of intersection will become the solutions. So I'm going to have an infinite number of intersections. So this is one solution, lambda 1b. This is another solution, lambda 2b. Third solution. And so on, and these are called the eigenvalues of the problem. Okay? So I have an infinite number of them, and so I can now write my solution as the following. Once again, we are not going to go into the details of these things. I'm going to do some hand waving from now on. Okay? So I have and I'm going to write the general solution as the following. So theta of x comma t is summation n is equal to 1 to infinity e to the power minus alpha lambda n t this unknown coefficient a n, which we have not yet calculated, and you know that they cancelled off on both sides here. I forgot to write it, but you can write that. We don't know that. The initial conditions will give us the answer. And then cosine lambda nx. If I substitute the initial condition, it is called as the making of a Fourier series expansion. Not going to do that. Not interested in the solution. But here is the thing that I want to point out. You see, the value of lambda b keeps increasing as I keep going further and further into the solution space. Which means that if I look at the quantity cosine lambda b, the value of this quantity keeps decreasing as the value of lambda b increases. Does this make sense to everybody? So for me, this is of course a series solution. But let's say that I am interested only in the most dominant of this term. Then I can say, if there is any mathematician in this room, they'll be spinning. But pardon me for this. This is approximately a minus alpha lambda square t cosine lambda x, where I'm just using the first root, which is the largest of the values. Okay, so if you want, you can call that as lambda 1 for all that we care. So this is because as lambda x increases for a constant x, cosine lambda x decreases, and the rest of the terms in a series I am essentially ignoring it. So this is an order of magnitude estimate. This is non-rigorous, but this is the least painful way. Okay? And now we come to the clincher for the argument as to why we are doing all this garbage, is because my aim is to say that, okay, the temperature variation within the body, the gradient has to be very small for zero-dimensional transient conduction. So what is small is a good question. One can typically say that a 5% variation between the centerline temperature and the temperature at the outermost end of the slab is reasonable. Okay, 5%, 2%, 1%, depends on what person you are. For me, 5% is good. Okay, so say 5% variation in theta between theta at x is equal to 0 and theta at x is equal to b is reasonable to say 0 dimension conduction, and keep in mind that we have this nice relationship sitting here. Okay? So what's a 5% variation? I'm going to write it out. Theta at x is equal to 0 minus theta at x is equal to b divided by x is equal to 0 is 0.05. And that's a 5% variation. I'm going to clear some parts of this board here, except for the bracket term. If I do the substitutions for theta at x is equal to 0 and x is equal to b, I end up getting the following. So when x is equal to 0, cosine lambda x is 1. So I have A e to the power minus alpha lambda square t minus, when x is equal to b, I'm ending up with cosine lambda. So A minus alpha lambda square t cosine lambda b. All of this divided by the same factor a e to the power minus something. This is equal to 0.05. I can cancel off a e to the power something on all sides here. And so I end up with the following. So 1 minus cosine lambda b is 0.05. Or cosine lambda b is 0.95, or lambda b is cos inverse of 0.95, which is approximately 0.3 radians. I just saw it today morning. Lambda b cosine inverse of 0.95 is 0.32 radians. So if lambda b is approximately 0.32 radians, I can say that zero-dimensional conduction is fine. That has still not solved my problem. I need to look at the Biot number, because the Biot number is the common factor between one-dimensional and zero-dimensional conduction. I see that in both the equations, both the solutions. So if I take this and substitute here cotangent of 0.32 radians for 0d conduction is equal to divided by the Biot number, and if you do the math, this is approximately 0.1, which is what you perhaps may have seen in your system dynamics course, where they tell you it's 0.1 and they tell you it's empirical. It's not empirical, it's analytical. We just proved it. And consistently experiments can prove that, okay, if you are within this limit of the Biot number, you can assume that the conduction is independent of the spatial dimension. This is the mathematical reasoning. The physical reasoning, we already looked at it. The Biot number is the ratio of our conduction to convection, and a smaller Biot number requires that the conductive resistance to heat transfer is lesser than the convective resistance, so we can say that the gradients are more or less uniform inside. Gradients are zero inside. Okay? So for any problem, if there is a time element involved, we are going to do the following. So this proves the criterion. So for any transient problem, first obtain the Biot number, given the parameters of the problem. This is some h times LC by K. LC is volume by the surface area. Because if I have a cube, the volume is L cube, the surface area is 6 times L square, so this characteristic length becomes L divided by 6. Something of that sort. If I have a sphere, I have to do something similar. Then if the Biot number is less than 0.1, which is what we have said, then there is less than a 5% variation within the temperature inside the body, and so we can assume a 0D conduction, and so we ignore spatial dimensions. And so what I'm going to do next is, in the next 7 minutes left, I'm going to set up the most general form of zero-dimensional conduction, including the effects of convection, including the effects of energy generation, and including the effects of radiation heat transfer. We will see what is the most general equation that we end up with, and then we will start making some assumptions and say, okay, if you neglect radiation, what happens? If you neglect convection, what happens? If you neglect everything, what happens? Alright, so here is the setup. So back to 0D conduction. And I want to see if there are any questions in our argument so far. We started off by saying temperature gradients are zero, and that's a situation of zero-dimensional conduction. Then we said, okay, what's the mathematical basis for saying that I have zero-dimensional conduction? I start with 1D conduction, unsteady, go through the solution process, separation of variables, solve the PDE partially, and obtain a criterion that says that if I figure out that this guy is 0.1 or lesser, I have a 5% or lower variation in the temperature within the body. And I'm assuming a uniform slab. I can assume a sphere or a cylinder, I'll get something similar. Okay, so it does not change my solution. Yes, question.
For question, what would it give us? Obviously it wouldn't give us a 1D, like, would it just give us a T of X at one point, or T of T?
Which one will give you what?
The 0D conduction.
0D conduction tells you that temperature is a function of time only.
Just time? So
Absolutely, yeah. Zero dimensions means no spatial dimensions, only time.
Okay.
Okay? So that's what we started off with at the beginning of class. So that solution there, that's 0D conduction. So essentially I'm just starting off with something, going off track, and then saying, okay, hey, this is where we started. Yes.
So if we went to two-dimensional unsteady, that would further complicate the Fourier series and...
Absolutely, solution will be very messy. And that is also under very special circumstances you can get this closed form solution. You know, if you start including thermal radiation effects, that's a nonlinear PDE there. Right, T to the power 4 and so on. Right? And heat generation and everything, you start including those kinds of effects, the solution is going to get really messy. And so people go for finite element or boundary element methods. So which is why I said this is under a very simplistic situation. Of course, we can find the solution for 1D under more complicated situations. That's not a big deal. We can still do that. We can still end up with the same criteria. Alright, so I'm going to start off here by saying this is a lump which is now a function of time only. So when I say zero-dimensional conduction, it means that it's unsteady first of all, and it's a function of time only. Okay, so here t is a function of time, so I have t as a function of time inside. Surrounding temperature, T surrounding, then I have ambient temperature T infinity, and H and so on, and then I'm going to have energy generation within this lump, so E dot G is not zero, and I'm going to assume the following. Okay? So T function of time, I'm going to assume that the surface is very large, so large enclosure gray surface. And we'll see the real meaning of gray in the weeks coming ahead. Okay, so this implies that alpha is equal to epsilon. I'm jogging your memories back to radiation now. And if I then set up the control surface around this lump, yes, I'm just going to draw that here. I'm going to assume that the initial temperature is lower than ambient. Does not really matter. It is T naught is less than T infinity and T surrounding. Then I start looking at things coming in and things going out. I have energy generation with it. There is a rate of change of stored energy within the control group. Then I'm going to have convective heat transfer in. So Q convection. When you think of radiation, there are two things happening. One is there is radiant flux which is emitted by the body as a function of its temperature. So this is the flux times the surface area. E times A suffix S. Then there is also irradiation from the surroundings, out of which a portion is absorbed. So that's alpha times G. And if I set up everything, Q dot is 0, so energy generation is present. So E dot G, I'm going to say, is Q dot times the volume of the body. And so, first law, E dot stored, E dot in, E dot out, plus or minus E dot generated, but let's assume plus E dot G, doesn't matter.